Hi, in the previous video to do with power supply input power stages, we looked at the various components of a power supply, including the transformers, full wedge bridge rectification, smoothing capacitors, and had a brief discussion about how to pick the right transformer for your project, all based on what power you want and volts and current and things. And also some of the things you need to watch out for as far as even things like the bridge rectifiers having to have heat sinks in the case of high power situations. In this video I'm going to look at showing, first of all I'm going to show you the circuit diagram that relates to the power supply, but also try to answer one of the questions that I've been asked a few times on either the forum or through Element 14, and that is that when you're using an N-channel MOSFET for your output stage, how do you get your drive voltage in excess of the supply rail for enabling you to turn on the MOSFET? Because if you remember from the previous videos, when you're driving a MOSFET, you have to take its gate for the N-channel ones 3, 4, 5 up to a maximum of about 9 volts above the source in order to turn it on fully. So if you have a main power supply rail of approximately 30 volts and you want to get as much of that as possible to your output terminals, you need to turn your MOSFET hard on. And the only way you can do that is to take the gate voltage above the source voltage, and that means going above the, in this case, 30 volts that would normally be part of your supply rail. So what we're going to look at in this video is quickly go over what it would take to create that additional voltage and have it applied to the system so that you can use it with your control circuitry. And what we're going to do for this one is we're going to look at the classic voltage doubler circuit and how you would hook that into here. And it only takes a few capacitors and diodes and a regulator in order to complete that stage. And so yeah, we're going to go have a look at that right now. So let's go back to the drawing board to start with, and we'll just plan it out first, and then I'll build up a test board and show you it working and show you the different waveforms and basically try to explain how it's going to be functioning. So before we look, when we were looking at the actual circuit, I didn't actually present a circuit diagram to you, so what I'm going to do is quickly draw one up on my tablet for you so we can just quickly discuss how it was working and how we're going to extend the circuit for getting this elevated voltage. So the first thing we had is an input transformer, which was mains on one side, so in my case 120 volts AC, and then the other side we had a pair of transformer windings with a 10-to-1 ratio basically here, which gave us 12 volts AC on each of these. Now we connected these together and then we went through a bridge rectifier. So a bridge rectifier basically is 4 diodes configured such that it will give you a DC output. So the power will come through the diode, come out here, go through your circuit to the negative, and then come back and go down to the negative side. So this is your negative terminal for your rectifier. And when the mains goes the other way, we'll go through here and up to here. So we have a bridge rectifier circuit in this here, and then we put a 20,000 microfarads of smoothing capacitors on here. And what would normally happen after that is you would have your MOSFET connected. I'm just doing a simplified diagram, and that would go to your control. All right, and this would be your output. Now if this is sitting at 30 volts and you want to have 30 volts on the output, how do you get that? Because it means that you have to take this above 30 volts, and that's not possible with the current circuits that we've been looking at. So what we have to do now is we have to build a mechanism to get that extra voltage for our control system, and the one I'm going to show you right now is going to be the voltage doubler. The way that works is you tap off of your AC supply and you build a voltage doubler to it. So you've already got effectively an oscillation running at 50 or 60 Hertz with your 24 volts, and we want to basically get twice that out. The voltage doubler circuit, I'm just going to erase this so that you can see, get rid of some of this other stuff out the way. So how does a voltage doubler work? Well, let's just take the AC input from our power supply. We'll draw in our bridge rectifier that we had, just so we got some context of what we're doing here. I'm just drawing it in a slightly different configuration. So this is our positive output from the bridge rectifier, and then our negative output will be on the other side from here. And this one is our, so this is our standard output with a full wave bridge rectifier. So our mains is, AC is coming in on these two terminals here. We're full wave rectifying it, and we've got our DC output here at, say, 24 volts under load. All right. Now, obviously, we need to have significantly more than that in order to be able to drive the output stage to full. So the voltage doubler basically takes the AC, because you've got this AC frequency coming in here, and it's going to, first of all, it level shifts it so that there is no negative part to it. It does that by taking the AC content, feeding it through a diode, all right, on one side, and on the other side of the AC. So if I just get rid of this piece of DC circuitry here, just for the sake of the drawing, we put a capacitor right across here. Now what's going to happen is you've got your AC voltage coming here, which is centered on 0, and the same on this side, it's centered on 0, but obviously the opposite way around. Because of the diode, it only lets it go one way. So when this is on the high side, it's going to pump the voltage through and charge this side of the capacitor up. This side is just going to stay low. On the other cycle, it's not going to be able to do anything, because this capacitor is blocked because of this diode. So it can't actually discharge it the other way. So you can actually even use electrolytic capacitors here because it won't charge it the wrong way. Now, because it's pushing through here, basically it's going to charge this side of the capacitor up to the peak voltage of what's on this side. So let's just keep the math simple, and we'll just say that goes up to 15 volts on here. So this is 12 volts AC. Now on this side, actually just forget the voltage for a moment. So what's going to happen is it's going to level shift this, because it's going to charge this up, but the other side is going to, the signal is going to still get reflected on here, but it's not going to come back through here. So what happens is this ends up being pushed up onto a 0 offset. So your AC here now is actually, instead of being centered around 0, it's now going to be sitting on top of 0. All right, so this is still 12 volts AC, but now instead of being centered on 0, it's now above 0 all the time, or just touching 0. Okay, and now what you do with this thing, so that now you've got effectively twice the volts peak-wise, because remember this was plus 12, minus 12. Now you've got plus 24 to 0. All right, so you effectively already now got double the voltage. And what you then do is put another diode in here to block it. And now you can put another smoothing capacitor, and what this one would do is, where is it? Here, this is your 0 volts. All right, you take this to the 0 volt line, and what's going to happen now is, because this has been level shifted, the voltage that appears on this pin here is actually going to be, so say this one on the output of this was 12, so that was 24 volts. Sorry, wrong one. I took it out, didn't I? The one from here was 24 volts. Then this is actually now going to be sitting at basically 48 volts. All right, so it's effectively double the voltage. And the way that it's done that, as I said before, is it simply level shifted the 12 volts AC, which was centered around 0, and it's pushed it up through the diode and the capacitor here to be sitting on 0 instead of around 0, which effectively now gives you double the voltage. And if you put a regulator on the output of this, all right, and say this is a 12 volt regulator, then and you set this, the ground reference of this one, on the positive of your supply, so maybe this is at 24 volts, all right, which is what came out of your standard power regulation, rectification. and now this is actually sitting 12 volts above that, which means that it's sitting at about 36 volts. All right, which is great. Now all we've done is we've added 2 diodes, 2 capacitors, and a voltage regulator. Now you'll probably have a little capacitor on the output of the voltage regulator as well, but that's really it. So you've got a bare minimum of components, and you've now managed to get yourself an extra amount of supply that you can use to drive your gate of your MOSFET well above the 0 volt line, the general supply line of your system. So let's just go to an actual practical demonstration of that. I'm going to hook into the transformer that I was using before, and let's see if we can actually make this happen. All right, so let's just go to the board. I've already made one up now, so I'm just going to put that into camera and power it up, and we'll go through with the oscilloscope, and I can show you these waveforms that are occurring. Okay, so I've built a small board that actually replicates the circuit I just doodled on the surface a moment ago, and what it basically has here, if I just tip it up a little bit to show you, is I've got the AC input, which is the 24 volts from the transformer. I have the capacitor, which is connected to one side of the AC, and the diode, which was the other one. I'll go back to the diagram in a moment, which come together at the juncture of the two. That then forwards through the second diode. So at this point here, it's level shifted. So what we should see on this side, if we probe here with the oscilloscope in a moment, you'll see that it's fully AC and centered around 0. So it's going plus 12, minus 12. On this side, we should see that it is level shifted itself, so that it's now sitting on 0 volts. And then on this end, we should see that it now has also been smoothed and rectified when you compare it on the 0 volt side of things. This regulator here is a 12 volt regulator, 7812, and the output of that comes across to this, and I've got a 1K resistor just acting as a small dummy load for it right now. So let's get the oscilloscope hooked up, and let's start seeing what waveforms we can see. Let me just bring you up to my tablet again. What I've done is my tablet's browsing to my Tektronix MDO 3000 oscilloscope, so I've got less movement to do. It's just reflecting whatever I set up on the oscilloscope is going to be reflected on here. As you can see, I'm adjusting the oscilloscope settings right now, and it's immediately being seen by the tablet, so we can easily watch what's going on. So alright, I've got the power turned back on. So with my oscilloscope here, the first thing I'm going to put on here is I'm going to hook it up to the AC input of the voltage doubler circuit, just so you can see what's coming in here. So that's exceeding the capabilities of the scope right now, so I'll make it 10 volts per division, and you'll see that it's just fitting in. If I get rid of the menu, you can see that is 28.07 volts. So it's got no load on again, so that's why the volts are slightly higher. If I just take my little resistor just for a second, just to put a load on here, you'll see it'll drop to a, right, so it's now clipped, and it's actually now only going up to 21.36, so it's a little bit overloading. I'm not sure why it's flattening on the top and bottom. That's probably because I'm exceeding the current capabilities of the transformer, and it's probably not able to keep up with it or something like that, because there's no rectification or anything else going on there, so it shouldn't be really that flat. So it has to be something else. Anyway, probably, as I said, probably because I'm overloading the transformer. So I'm going to take that back off again for the moment before it starts to smoke and burn me. And we'll just do this with the open, no load situation. So that's our input voltage to the voltage doubler. As you can see, 28.02 volts, and it is centered around 0. So this marker here tells you that it's centered around 0. All right. So I'm going to change the range now for this next step to 20 volts per division, because it is going to change what we see slightly, and I'm going to drop down the 0 reference to at least a 1 graticule further down. so you have a bit more room to play with. All right, so if I go on my, actually if I on my display here, if I go back to where was I? Oh, OneNote. So what we've got here is the AC voltage centered around 0, and it's 28 point, well, near enough 28 volts AC. Okay, so that's what we have for now. Now what I'm going to now do is, that's at this point here, measured here and here. So that's what we just measured. Now what I'm going to do is I'm going to make another measurement here. So I'm going to just change to a different color. And I'm actually going to now probe at this point here. Now what we should see there is it level shifted, all right? But nothing else. It should just be level shifted, but be pretty much the same waveform. So I'm on the other end of the capacitor now. Let me just go back to the display. So I'm on the other side of the capacitor now. Let me just put it back again just to show you the difference as I connect. So this is on the input side, and you can see my 0 line is shifted. It's down, this one graticule down. Okay. Actually, if I just make it easy for everybody, I'll just center it on the brighter center graticule. So now I'm going to shift the oscilloscope probe now to the other side of the capacitor. All right. Now you can see it's instantly now been shifted. It was 28 volts before, and now it's gone to 47 volts, but it's also now, as you can see, it's sitting on the 0 volt line instead of being equal either side of the 0 volt line. And that's pretty much that first diode and capacitor. That's what it's done with it. It's level shifted it now. So as you can see, we already now have a peak voltage way in above, because we're at 20 volts per division, so it's 20, 40, 60. It's almost 80 volts peak. So the one thing to bear in mind with this is that it's getting back to potentially mains voltage levels. So you do need to be aware of that fact and just tread carefully. All right, so let's just go back to our diagram. So what we've done now is we've measured here at this point here. So we measured between here and here, and what we got on this one is we got the same AC waveform, but it was actually sitting on 0 volts, making that line a bit too long. So it was actually sitting on 0 volts, and this is now 47 volts up here. All right, instead of 28 volts, we're now at 47 volts. So a little bit less because you got some diode drop and things like that as well, remember. So now that's pretty interesting. So that's actually shown that our level shifting has worked. Now the next step we're going to go is we're going to go and measure on this side of the diode here. And in order to do that, I actually have a different ground reference. If you remember on our AC circuitry, we had our full wave rectifier from the mains. All right, and then you've got your ground and your plus. All right, I'm just doing a short circuit kind of version of a full wave bridge rectifier. So that's our plus, and this is our 0 volts. And what we've got is this one is actually attached to here. So if you didn't have that attached, of course, you would not be able to read anything here because it would all be sitting at the same potential as this, so it just wouldn't work. Even though I've shown this as AC coming in here and we've pushed it up and level shifted it, I didn't have to worry about this one now. But now because I'm measuring here, if I go between here and here, it should still give me a reading. And because of this, it actually shows that my ground, because it's coming through here, and then it's going to go back through the bridge rectifier that we had in the main power supply circuit and back to where it came from. So it does have a path to get back again. All right, so now I'm going to move the oscilloscope to the other point on the display, and we'll see where we get to. All right, so as you can see here, it looks a little odd because we're actually still got one end on the AC side of the input rather than the ground reference side. So it looks a little odd because you've got the AC having an impact on it. But what you can see now is it's no longer going all the way to ground. If I go back again for a second, you'll see that's what we had before, where it's all going from 0 volts to 47, 48 volts. And on the other side of that second diode, it is now, it's slightly higher average voltage, because obviously it's reading the average, and now that there's some smoothing involved, it's offsetting this reading slightly. So as you can see here, it is sitting now at about 40 volts odd before you even account for these. So it's still 20, 40, 60, so it's still 80 volts. So the peak voltage hasn't changed here, but it's got now a heavy DC content to it. And that's just because we're still measuring, if I go back to the diagram, we're still measuring between here and here at the moment, between this point here and this point here. So we have a heavy AC content on this part of it, so that's why you've got that extra offset. So what I'm now going to do is I'm going to now move my ground probe of the oscilloscope to here. And this is where one of the benefits of having an isolated power supply is that because even though I'm moving the ground to something that's not really the true ground or the AC coupled piece, it's still not going to affect anything. So that's one of the reasons why it's good not to have your oscilloscope connected to ground, or sorry, your power supply, by having it floating. So I'm just going to connect this now to the ground point, which is actually one of the wires I brought out to the edge, and we'll see what we've got. Alright, so I've now moved my ground point to move my ground point to here. So what we're now doing is we're monitoring, let me just change different color just for drawing. So now we're monitoring between here and here. Alright, so let's see what waveform we now get. Okay, let's just switch back to the oscilloscope. So my Tektronix is now showing that we have 74.91 volts. That's quite a lot of volts, but you can see here there's very, very little DC or AC content to it. There is a slight bit of AC content, and if I change the settings of the oscilloscope input to be AC coupled for a second and crank up the resolution of the, right? So you can see that we have, this is at 500 millivolts, so we have about 1 volt peak to peak now, but it's sitting on a total voltage of 70 volts, so really it's not going to have much of an impact on anything. Alright, so if I go back to DC coupled and crank the volts back down, there we go. So you can see it's very little AC content in here. We've now got 74 volts available to us. So instead of having the 28 volts of the main power supply, if I just take one of my meters, and I'm just going to measure the actual DC voltage right now of the on the capacitors of the output. All right, what I'm reading right now is 37 volts. Again, there's no load on these systems, so it's quite high. So 37, that's if you double that, because remember this is a voltage doubler circuit, so our smoothed and rectified 24 volts from the transformer is giving us 37 volts DC at the moment on the end of the capacitors, and our voltage doubler is giving us 74 volts. That's pretty a pretty accurate voltage doubling, you know, when you consider that it's just made from a handful of cheapy components and things like that. Now, the one thing you need to bear in mind is that your circuit, you know, even though going back down to this a second, there we go. Even though within this, you know, you're still only dealing with 30 odd volts and things like that, you've actually doubled your voltage now. So you've got the 75 volts sitting on here. My actual capacitors, which I'm actually going to have to do it, if I'm going to do a real one of these for my power supply, then I'm going to have to make sure I get better capacitors, because these are actually only rated at 63 volts. So I'm actually exceeding their voltage rating slightly, which is not good. So for the sake of this demo, I'm just going to ignore that for now. But obviously for anything that you're going to be building as part of your circuitry, you need to make sure you have probably at least 100 volt capacitors used in your voltage doubler circuit if you're going from 12012 or 15015 transformer. As you can imagine, if I actually had the 15 volt transformer here connected up, I'd probably be sitting at close to 100 volts at this point right now. So anyway, we're now voltage doubled, we've now smoothed, so now we have a significant increase in volts for driving the gate. Now we got way more than we actually need for driving the gate here, so we have to actually look at doing something a little different. So that's why we have the regulator. So I've attached the ground pin now of the scope to the 0 volt of the 12 volt regulator, and I have the probe attached to the input to the oscilloscope, sorry, the input of the regulator. So let's have a look at what we have now. Alright, so looking at the oscilloscope, I haven't connected the ground of the voltage doubler regulator yet to the power supply. I'm just about to do that now, and you'll see this will actually then give you a proper voltage reference to look at. So I've just connected it. So you can see now it's sitting on the input to the regulator at about 15 volts. Now part of that is because there's a bit of bleed because there's no load into the power supply. So I've just put the 10 ohm load resistor on there now, and you can see that the input to this, now that I've loaded it heavily, is actually not quite enough to give me a voltage regulator output. As you can see, I only had, sorry, my clip just dropped off. You can see I've only got 11.3 volts on the input, which means that on the output of the regulator it's sitting at only 9 volts because it's not a low dropout regulator. And what would probably be better there is a 5 volt regulator or something like that, because that's really all you need. If I take the heavy load off, because I'm actually putting quite a significant load on the power supply now, dropping its volts on the transformer, you can see now I'm getting about 10.5 volts there on the output, and the input to that regulator is now probably jumped up considerably. Yeah, it's not a huge amount actually. It's still sitting at about 11, 12 volts. Now one of the things that I've discovered here, which I'll tell you about, is with this circuitry, without any load on the power supply, now this is normally you'd have some load because even your control circuitry would provide a load, the voltage on the power supply actually slowly drifts up, and this I think is attributed to the fact that this regulator has a quiescent current of about somewhere between 6 and 10 milliamps, depending on where you buy it from and whose it is. And I've got a 1K on the output of the regulator, but even other circuits using, say, an LM317 or something like that, you would still have about a K as part of your voltage reference from the output dividing down to your VREF input, which means that you're still going to have quite a few milliamps of draw on the circuit. So the issue with that is, where is that current going? It's actually going to the positive side of the capacitor, like your main power supply capacitors. So if I just change my view for a moment to one of my meters that I've got hooked up to the power supply, actually I'll just leave it here and I'll hook up the scope to that. It's easier because we've already got that in view. So let me just disconnect this off of there, and I'm now connecting the oscilloscope DVM. That's one nice thing about these Tektronix MD-3000s is they've got this built-in digital multimeter capability as well. So not only can you look at the waveform at exactly the same time, you can make some half-decent measurements of the voltage and things like that, as well as seeing what it's doing. So right now I've connected that across the power supply, and as you can see, that is a significantly higher voltage than what it's supposed to be. If I just put the load on there for a second, you can see I just dropped it on there. It's on there now. And you can see it's now dropped down to the 24 or 23 and a bit volts. That's overloading it slightly. So if I just take this off, right, and just leave that there, you can see it's drifted up to about 38 volts, which is okay, and it's pretty much sitting there. It's not really going up anything significant, and that's the voltage doubler ground of the output of the regulator is not connected to anything yet. So all there is the circuitry that's working on the AC side of it. Now if I connect the ground of the voltage regulator, which effectively elevates it effectively allows the regulator to do its job, to the positive of the capacitors, all right, you'll see what happens here, right? This is fairly stably sitting there at 37.86 volts. disconnected it now. See that quite rapidly, and this is just based on, as I say, about somewhere between 5 and 10 milliamps of current flowing through the regulator just for its quiescent load, because there's only a 1K on its output, which is not a lot. It's drifting up now, and it will keep going until basically the regulator doesn't have any more room for regulating. It'll just drift right up there to the 60 odd volts. Well, my capacitors on this power supply are rated at 68 volts or something like that, which normally would be perfectly fine. But in this case, as you can see, if you're not careful, you can rapidly get up to some significant voltages if you make the wrong connections or if you don't have any load. Now this is because, as I said, there is no load whatsoever on the output of these caps, so even a small leakage from the voltage doubler through into the capacitors, which is not really leakage, it's just the current from what it's doing, is elevating this. It's already, see now it's already over 60 volts on there, which is quite concerning when you do this kind of circuitry. But if I just for a moment connect the load back on, you can see it immediately drops right back down to where it should be. So it's not a huge amount. It's, as I say, it's just the quiescent current of the regulator that's causing this. But if you don't know that that's happening, you could get thrown and try to wonder what the heck's going on with your circuit. So yes, voltage doublers work and everything else, but you do need to be wary of the fact that they can, under no load circumstances, and if you don't have any internal load for your control system, drift the voltage up slowly on your power supply. And if you've got amplifiers and things like that that are limited to say 40 volts, and you're working on a circuit that, like there, is only designed to have 24, 25 volts, then it's like, well, that's fine, I've got plenty of headroom. But if you don't have enough load, then it's going to start creeping up, and very rapidly, as you can see there, it'll get to 40 volts and then start going above that and potentially could damage something. Now, like I said, I don't have any control circuitry that is governed by that, but I wanted to show you how a voltage doubler works. But this is one of the pitfalls you need to watch out for when you're introducing it into your system, is that if you don't have any load, it can start effectively charging up your main power capacitors just because of its quiescent current. So that's about it for now. I hope you've learned a bit about voltage doublers and how you can get the extra voltage you require for your high side N-channel MOSFET driving. It's, you know, that's one option. One of the other things you can actually do is to use a separate power supply. All right. I mean, you know, my transformer here has got 12012 output, but you can actually just get a tiny transformer that just gives you a 9 volts at say 100 milliamps output, and that would be more than enough to do this, and then you wouldn't have this issue about it slowly charging up the capacitors or anything. And what I'll do is, I've got some here that, again, Element 14 is sponsoring this project, have sent me, and I'll just grab them and show you them. There we go. So for a bit of context, I put them next to the voltage doubler circuit that I built. So you can see, size-wise, they're actually smaller than the area taken up by the voltage doubler. And what these things are, they're a completely self-contained unit. They've only got 4 pins on the bottom, and same as this one. All right. And these both cost under $10 each. I think the smaller one is $8 and something Canadian. So US wise, it's probably going to be slightly cheaper. And this one is a 5 volt here, is a 5 volt at 200 milliamps. And it can take anything from 100 volts to 240 volts AC as its input. And it's very easy to just PC mount them because they have the just 4 pins. Can go directly onto VeriBoard or PC board or something like that. Now, of course, it's mains input on one side, so again, if you're not comfortable with this, then don't. But you know, if you're going to be building your circuit boards up and you're building your own power supply, then of course, you know, this is a very viable option. And if you're only building one off, you know, to be honest, less than $10, and if you're ordering parts anyway, is it really worth the time and effort to build a voltage doubler? I mean, it's nice to do that and everything, and it gives you the experience and the knowledge of how voltage doublers work, But as you can see, if you don't compensate for the fact that you can get this quiescent current drifting through, it can interfere with your theoretically stable voltage on your main power supply. It'll slowly drift it up in very, very low current situations. Obviously, the minute you put anything of a half decent load on your power supply, then there's not going to be any issues. But if you want to avoid that altogether, then an easier method to do is to use one of these things. Now, what's the difference between those two things? They're both available from Element 14 or Newark or Farnell's, and this one is a 5 volts 200 milliamps, and this one is a 15 volts 200 milliamps. Outside of that, you know, obviously the pins are a bit bigger on the bottom, but everything is built into this to be able to give you straight from mains input to your nice smooth DC output. All right. So in my book, these are a far, far simpler option to use when you're building a power supply and you want to get that extra supply jack up on your positive rail. You just have one of these tiny devices. You can just put it onto the circuit board design, and then you just, you take the 0 volt output and you connect that to the 30 volt supply or 24 volts or whatever it is, and you put your 15 volts, or you can get these in a number of different voltages: 3.3, 5, 6, 9, 15, 12 volts, whatever you need. And so I would suggest something probably around about a 9 volt one would be all you need. And as I said, even the 15 volts at 200 milliamps is under $10, and the 5 volt one at 200 milliamps was $8 and something. So they're easy, basically hassle-free. You don't have to design everything; it's already done, and you just hook it up and away you go. And you won't have the same issues with these, with the bleed current changing the voltage on your regulators. Now, I don't have a circuit board to hook these up right now, so I'm not going to just have them hanging in air, because that would be demonstrating a very bad practice, because this is, as I said, mains voltage on one side of these and you're 15 volts out. So later on, once I get a circuit board built up, I will include these on, and at that point we will have a look at how well they do or don't work. But for now, that actually, gives you the feel of what you can do as far as driving the high side N-channel MOSFETs. As I said, my preference would be just to go to one of these things. The voltage doubler circuitry, I've seen people use them. Some of the other power supply projects on the internet have used voltage doublers to get that extra voltage too, but they either didn't experience the issue that I just demonstrated to you, or because they had additional load because of the rest of the circuitry, they may not have even realized that the potential of it happening is there, and they just went on anyway because there was enough of a load in the system that it prevented it from causing any issues. Anyway, that's it for the power supply side of things. I think the next video is probably, although I'm not going to promise it because I've actually got some things out of order in the past, and that kind of upsets people sometimes. But we need to now look at getting all these different pieces put together. I know we've already done one as a basic analog system, but I didn't have the power side of it, and we didn't try and load it up and see how well it performs either. So my next task will be to put something together for that. I think before that happens, I've got a couple of other videos I need to do. So there is going to be one on using a microcontroller to read the voltages and things. Anyway, that's all for future videos. So for now, I'm going to sign off here. As usual, if you have any questions, just post them in the comment section on YouTube and or in the forums on Element 14, and either myself or one of my colleagues will get back to you and answer your questions. As I said, the way that I've done this is not the way you would normally do it. Whilst I've taken every precaution with the mains and everything else, I do know what I'm doing, and I have many, many, many years of experience. So I don't regard that as a risk for myself. But if you're going to do this, then, as I said, somebody needs to be with you that is qualified and has the training to deal with main size voltages and get everything hooked up in a safe manner. And if in doubt, just go the route of using a second-hand power brick from a laptop or something like that, and it will give you more than you need. or the other alternative to minimize the risk to yourself is to just buy a a 24 volt or 30 volt DC power adapter, so mains in and 24 volts DC out, and then just focus on the control circuitry and everything else for the power supply. Some of the future projects we're going to do, like the DC load and things like that, you can actually even run them off of a battery if you wanted to, because the control circuitry and the displays won't consume a huge amount of power. And if you're using, say, LiPo or something like that, it probably would be able to run it for quite a number of hours on a single charge without any issues. So that's just a choice of how you build it and everything else. Obviously, with a power supply like this, where you need to be able to provide a number of amps, then of course you're not going to be drawing that up with a battery unless you're hooking up a car battery or something ridiculous like that. Anyway, I hope you enjoyed it. Give me a like or a thumbs up or whatever is appropriate depending on where you're watching it from, and I'll bring the next one to you real soon. Thanks, bye.